There we are. Okay. So we have potential point charges. We start with a single charge. Then we have multiple charges, and then we're going to compare our voltage and our electric field. So here's our charge with an electric field around it, and we bring a point charge. To get a point charge in here, we've taken it from somewhere else, and it works its way in to get to that spot, which is the distance away from the source. Our change in potential then is given by this. It's negative integral of E dot ds, okay, which in this case, so we kind of blew through the math of this last time, and so we're going to do it more rigorously here. Okay, well, our field is going to give us KQ over R squared. Okay, that is in the r hat direction, right? And it's a dot product with our differential change in our path. Okay, well, let's take this part over here off to the side, that r dot ds, which we had a little bit of confusion on the other day. R is just, I'm sorry, not r hat, this is r hat here. This is the value of this is just 1, okay, times ds cosine theta. Okay, but this, if it's along cosine theta, then cosine theta just equals dr, and that turns this whole thing into dr. Now we can adjust, this becomes dr, and we get negative kq integral of, and we're going to go from r initial to r final, where our starting and finishing points are, r negative 2 dr. So we pull the kq out, okay, and we're left behind with the r2, okay, in the denominator, which becomes r to the minus 2, and this just becomes dr. And this is a relatively simple integral from here on out, because this just becomes our delta v equals negative kq. Okay, this is negative 1 over r, evaluated from r initial to r final. Negative can pull out, so we get kq, and in brackets we're going to have 1 over r final minus 1 over r initial. All right. But where did we start? Remember, we moved this. Yeah, we moved this test charge in from an infinite distance away. Well, if our initial r is infinite, 1 over infinity is ostensibly 0, so this goes to 0 if we start from infinite distance away, and our voltage equals kq over r, which is just the distance that we are away from our from our original amount. All right. Now, our U, our potential, is equal to Q naught. Our potential energy is equal to Q naught, okay, whatever that charge is, right? Because our potential is, this is the work done per unit charge, right? We defined voltage as work done per unit charge. Okay, well, if it's work done per unit charge, and we multiply it by the charge of the test charge, by however much that is, okay, that gives us our potential, right? Our potential energy. Okay, that's the potential energy of this thing, because that's how we got to that point. All right, well, this just equals Q naught times KQ over R, right? Well, then it becomes KQ Q naught over R. Then does that look kind of familiar to you guys? Right. This is our potential energy for the potential energy for two charges that are near each other, right? Okay. So that's where we're getting to this. Okay. So you guys good here? I need to go top of the page. Okay. So let's take two more charges. And that's going to be Q1. We've got a collection of charges there, and that is Q2. All right. These two are going to have, a potential energy between them, okay, or the amount of, any one of them has this potential energy, because to hold them in these spots, okay, if all of a sudden we let go, what are they going to do? Right, they're gonna fly apart. So there is a potential energy just in the fact that they're in proximity to each other gives them a potential energy with each other. So, and from down here we have that potential energy is going to equal K, which equals what, Ashmeet?
1 over 4 pi.
Okay. Q1, Q2 over K equals Q1, Q2 over R squared, and that's these guys right here, which is this R squared is the distance between these two guys. And so this is our potential energy, keeping these that they two have just for being in proximity with each other. Nick.
How do you measure the forces that keep two together? QE. Q times E.
Oh no, that keep the pluses. That keep these charges together on the point charge?
Yeah.
That is a real good question. It's remember what makes a plus charge. Okay, we're talking about matter, right? And our matter is made up of atoms, and atoms have nuclei, or the kernels, right, with their valence electrons. So this particle right here, in order to have gained a positive charge, had to have lost electrons. Okay, so whatever you have right here, whatever this thing is, it's lost a certain number of electrons. The whatever forces are keeping the structure together, okay, are at the atomic level, or we're talking like a chemical bond or something like that, and these forces are not strong enough. The abundance of a positive charge is not strong enough to rip the individual thing apart, if that's what you're going for. Does that answer your question?
Yeah.
Okay, Shmi.
Is it just R or R squared?
This is just R. Shoot. Okay, what is it if it was R squared?
That would have been Coulomb's law.
That would have been Coulomb's law, which means would have been the force, right? Okay. Yes, that was a typo.
And it's just
Okay, guys, we're not done yet. So
integral of Coulomb's law is that one, right? Wait.
integral of Coulomb's law over So for work equals force times distance. Yeah. So the integral of the force over the distance. Is that what you're?
Yeah, like you just multiply Coulomb's law by R all the time.
Essentially, yeah.
So we don't ever have to calculate the forces that I was talking about?
No. No.
That seemed pretty though.
No. The word then you start talking about energy in like kilojoules per mole and that sort of thing, and we're not. That's. Oh my gosh, that is so chemistry. So we're not dealing with that. Okay, so now we're going to deal with multiple charge. What if this happens with multiple charges? Okay, so. Okay, if this is multiple charges, so we've got a Q1. Let me find the pen that I want here. There you are. So we've got a charge there, and we've got one here, and let's put one here, and let's put one way up here. Q2, Q3, Q4, and it doesn't matter what charge they are. They could be positive, they could be negative. And then we bring in our test charge, and we'll put our test charge like right about here. Okay. There is going to be a potential energy and a voltage coming from each one of these. So we can cover up these guys, and there will be a electric potential for Q1. There'll be an electric potential for Q2. There'll be one for Q3, and there'll be one for Q4. Okay, and mercifully, okay, the total voltage equals the sum of the individual voltages. Oh, cool! Another summation. Okay, so our voltage then equals the sum of I equals 1 to n KQI over RI. But this is a scalar. This is important. It doesn't matter the direction. This is a scalar value. Energy, electric field, is not. Electric field, remember, is summation of I equals 1 to n of KQI over RI squared RI hat. And what gave us all the trouble with our electric field is this stupid R hat, because that changes, if we're coming over to our electric field, wherever we are, our electric field is changing direction wherever we are around the charge. But our voltage, if you're that distance away from the charge, you're at a particular voltage. If you're that distance away from the charge, you're at a different voltage. But this sphere, this line that we have, okay, this is in 3 dimensions, right? So it's really this surface that we have, okay? They all have the same potential. And we have a name for this, and this is called, an equipotential surface. Okay, and we can have these equipotential surfaces because, they are scalars. And an interesting thing that we'll get more into with the next lecture is that these equipotential surfaces are perpendicular to the field lines. Okay, so the surface itself will always be perpendicular to the electric field line at any given point. They are normal to each other. So that's really a pretty cool thing. And we're going to talk about that more with our next lecture. So you can kind of relate it like this. This is our scalar. This is our vector over here. Thank you. That's our scalar. That's our vector. Okay, you guys know what's our vector, Victor? Do you guys know that joke? We have Clarence. You don't know her? What's that from? It's from airplane. Good. Okay. Our potential energy. Okay. Is potential energy a vector or a scalar?
Vector.
It is also a vector.
What?
No, it's scalar. No, scalar. No, potential is a scalar. So,
Well, isn't it negative?
is there a direction to the potential energy?
But it has
Okay.
sign, right?
But what?
It has sign.
Oh, sure. Yeah, you can have different values of it. But that sign is based on an arbitrary position. So, okay. That U then is whatever our test charge is times, and that also makes this a scalar quantity right here. Okay, so next lecture we are going to get into the gradient, okay, which is really cool stuff, and it's how we're able to go from how we are able to determine our electric field based on our voltage at any particular point. But that is for next time, and that is it for potential and point charge. Question?
So, can you explain one more time talking about the equipotential surface?
Yes. Okay. Because voltage is a scalar, it doesn't matter where we are along this line right here. Okay, that there is a distance r, particularly if this is a uniformly distributed, a uniform electric field. That within this field there is a distance away from our point charge that we are going to have a potential that stays the same, right?
Because it's scalar.
Okay, because it's a scalar. So it doesn't matter where exactly we are around it as long as we're a certain distance from the center. Okay, so that concept that, if r is a constant, right, what can we make if r is the same the whole time? What shape is made from a constant radius? A circle, or in 3 dimensions, a sphere, right? So around a point charge, there is a spherical equipotential surface. Yeah, and as we move, so let's say this is 4 volts, and then we move further out, that would be 3 volts, right? And so these surfaces are equipotential. And the really cool thing is, all of these field lines coming out of this potential are radial, right? All the field lines come, if it's a point charge, all of the electric field lines are in direction of r hat, right? Any equipotential surface is perpendicular to r hat at any particular point. That make sense?
Yes.
Okay. Think of it this way. Are there any field lines going that direction on our equipotential surface? No. Right. Therefore we have no field in that direction. Okay, that equals 0. The fields are perpendicular to the surface at that particular point. Yeah? It's just like being tangent to a circle. Okay, I'm sorry, no, the radius is perpendicular to the tangent, right? So, same idea on a sphere. Okay, we good? Other questions on this?
The force E, the electric field line had the r squared, right? On the bottom.
Yes, electric field is r squared.
And
Yeah.
But the potential energy had r.
Electric field is r squared. Potential difference or electric potential and potential energy are, here's the potential energy, are both r.
This is like force and work.
Right.
So why are all the electric units why are they in unit per coulomb?
Why is
everything per coulomb?
it
Because it's like joule per coulomb.
right, think of them as, let's go back to a gravitational model here, just for a sec. Near the surface of the Earth, we have the value g, right? G is in meters per second, 9.8 meters per second squared. Okay. We could also write that as negative r hat. Okay. We could also write this, instead of meters per second squared, we could also write it as 9.8 newtons per kilogram, right?
Yeah.
Okay. So this all of a sudden becomes a force per unit mass. All right. And these, sort of like a Newton per coulomb for our electric field is newtons per coulomb, right? For our gravitational field, we have newtons per kilogram. And it's just, it is dependent upon the charge of the test charge, or this is dependent upon the mass of the test mass.
So does that mean that newtons can also be coulombs for right?
Maybe that's like a physical.
No. We're drawing an analogy here. Okay. All right, we're gonna turn this off here.